This video is about something called the squeeze theorem. I'm going to tell you what it is, and then I'm going to show you how we'd use it to prove an important trigonometric limit. The squeeze theorem says, given h of x is less than or equal to f of x, which is less than or equal to g of x, if the limit of function h as x approaches c equals the limit of g as x approaches c, then the limit of h equals the limit of g, which equals the limit of f as x approaches c. All right, let me try that again in English. Given a function f of x that is always between two other functions, h of x and g of x, if the limits of the two outer functions are equal, we're talking about h and g, if those are equal, then the limits of all three functions are going to be equal. Now here's a graphical representation of the squeeze theorem. Notice that we have this upper function g of x, and then we have this lower function h of x, where h of x is always less than or equal to g of x on this particular interval. Now, notice what's happening as the x values approach c. Notice that for both the upper function and the lower function, as we approach c, both functions have the same limit. Both functions are approaching the same y value. Now, if we have this middle function, f of x, that is always either between or equal to the upper and lower functions, it makes sense that if the upper function and the lower function approach the same value, then the middle function is going to have to approach that same value as well, because it's sandwiched in between the other two functions. It has no choice. If it's going to stay between the upper function and the lower function, if both functions approach a certain limit, then the middle function has to approach that same limit. Well, now I'm going to show you how to use the squeeze theorem to prove an important trigonometric limit. We're going to prove that the limit of sine x over x as x approaches 0 is equal to 1. At this point, don't worry if you're feeling like you couldn't come up with this proof on your own. For now, if you can just follow along and understand everything I do, you're where you need to be. For this proof, we are going to compare the areas of three different shapes that we've drawn here on a unit circle. So notice this is a unit circle. The radius here is 1. And imagine that this angle theta, which is in radians, could be anywhere in the first quadrant. Notice that the larger triangle shown here in yellow is the area of the larger triangle is always going to be bigger than the area of the blue sector, because the blue sector is completely inside of the yellow triangle. And now notice that there's a smaller green triangle that's inside of the blue sector. So the area of the green triangle will always be smaller than the blue sector. So we have area 1 is greater than or equal to area 2, which is greater than or equal to area 3. Let's come up with an expression for each one of these three areas. Starting with the yellow triangle, we know that the formula for the area of a triangle is 1/2 base times height. So that's going to be 1/2. The base of the triangle is 1. Now, what about the height of the triangle? We need an expression for the height of this triangle. For that, we're going to, let's call this height h for a moment. All right, I'm just going to temporarily call this h. Now, understand that this is a right triangle, so we can use the definitions of sine, cosine, or tangent. From the perspective of angle theta, this h is the opposite side, and the number 1 down here is the adjacent side. So we know that the tangent of angle theta is opposite over adjacent. So wouldn't the tangent of theta be h over 1, all right? Opposite over adjacent. Well, we don't need a 1 in the denominator, so if I kind of erase that, we find that the tangent of theta is equal to h. So in other words, the height of this triangle is tangent theta. So back to my expression for area. If I want to do 1/2 base times height, I can do 1/2 times 1 times tangent theta, because that is the height. Cleaning this up a little bit, we will have tangent theta over 2. So let's move on to the area of the sector. For this, we have to remember a formula that we learned in a previous class. So I'm going to say recall. When theta is given in radians, there's a formula that we're supposed to memorize. The area of the sector, which for some reason they often will use the letter S to represent the sector area. But the sector area is always going to be 1/2 r squared theta. All right, that's the formula for sector area when the angle theta is given in radians, which it is. So if we apply that, then an expression for this area will be 1/2 r squared, so that's going to be 1 squared times theta. So cleaning this up a little bit, of course, 1 squared is just 1, which isn't really doing anything. So we're just going to end up with theta over 2. All right, now for the third area expression. We know that, again, the area of a triangle is 1/2 base times height. So we're going to do 1/2, and 1 is the base. But what about that height? So here's the height that we're talking about right here. All right, we need some type of an expression for this height. So here's the key. Remember that this entire thing is based off the unit circle. So if you can understand that this point right here is this point right here on the unit circle. Now, here's something that you have to recall from your pre-calculus class. Any point on the unit circle is going to have the coordinates cosine theta, comma, sine theta. Every point on the unit circle is cosine, comma, sine. In other words, the x value is always cosine and the y value is always sine. So the only thing you need to realize is that the height of this point, the height of this triangle, is just going to be the y value of this point. And the y value is sine theta. So that means in terms of this triangle, the height of this triangle is sine theta. So back to our area expression, 1/2 base times height, it'll be 1/2 1 times sine theta. So cleaning this up a little bit, we're just going to have sine theta over 2. All right, so the first area is going to be greater than or equal to the second area, which is greater than or equal to the third area. If we multiply everything by 2, notice all of the expressions have a denominator of 2. So what happens if we multiply everything by 2? Well, notice that all of the 2's will simply cancel each other out. So that's going to give us this inequality right here. All the 2's are gone, so we just have tangent theta is greater than or equal to theta, which is greater than or equal to sine theta. Now, for reasons which will become clear in a moment, I would rather write tangent as sine over cosine, so we have this. So imagine I did the reciprocal of every expression in this inequality. That would be allowed. So the reciprocal of this sine over cosine, of course, would be cosine theta over sine theta. And then the reciprocal of theta would just be 1 over theta. And the reciprocal of sine theta would be 1 over sine theta. But be careful, if you take the reciprocal of all of these expressions, you will need to reverse the direction of the inequality. So instead of greater than or equal to, we will now have less than or equal to. Hopefully it made sense to you why we need to reverse the direction of the inequality. But here's a quick example just to make it super clear. What if I had 1/2 is greater than 1/3? We know this would be true. 1/2 is greater than 1/3. But if I took the reciprocal of both of these, that would be 2 and 3. Now, is 2 going to be greater than 3? Of course not. 2 is going to be less than 3. So this will always happen when you have an inequality. If you do the reciprocal, then you're going to need to reverse the direction of that inequality. What happens if we multiply through the inequality by sine theta? So I'm going to multiply every expression by sine theta and see what happens. Notice that right here, sine theta cancels out. And also the same thing happens here. Sine theta and sine theta cancel each other out. So that's just going to leave us with cosine theta. And in the middle, we have sine theta over theta. And then at the end, we just have 1. And the first expression is going to be less than or equal to the middle expression, which is less than or equal to 1. Let's take a second to remember what we're trying to do. We're trying to prove that the limit of sine x over x as x approaches 0 is equal to 1. So keep that in your mind, sine x over x. And here we have sine theta over theta, which is the same thing just with a different variable. So remember, we want the limit of this as, in this case, theta approaches 0. So let's go ahead and find the limit of all three expressions. So we're going to have the limit as, instead of x approaches 0, we'll say theta approaches 0, since that's the variable. But we'll have the limit of cosine theta, and that should be less than or equal to the limit as theta approaches 0 of sine theta over theta, which is less than or equal to the limit as theta approaches 0 of the number 1. So we should have asked this from the beginning. Why can't we just do direct substitution to find the limit of sine theta over theta? Well, if we substitute 0 in for theta, immediately that's going to be undefined. So that won't work. So that's why we had to use the squeeze theorem. Now that we've done all of this manipulation, we should be able to do direct substitution to find the first limit and to find the last limit. So if we do direct substitution right here, this should be the limit of cosine as theta approaches 0 should be the same thing as the cosine of 0. We're just doing direct substitution, putting 0 in for theta. All right, so that should be less than or equal to the limit as theta approaches 0 of sine theta over theta, which is less than or equal to. We learned early on that the limit of a constant is just that constant. So that's just going to be 1. So the only question is, what is the cosine of 0? Quick reminder, if I've got the unit circle, all right, and cosine, well, 0 on the unit circle is right here. Cosine is the x value on the unit circle. And of course, the radius of the unit circle is 1. So that means cosine is 1. The x value is 1. So this limit that we're looking for is squeezed in between 1 and 1. The limit is less than or equal to 1, but that limit is also greater than or equal to 1. The only way that happens is if the limit itself is equal to 1. Let's take a look back and see how the squeeze theorem has been applied. Remember that basically the squeeze theorem said if we have a middle function f of x that is always between two other functions h of x and g of x, then if the limit of the outer functions are equal, then all three of the limits are equal. And as you can see, the outer limits did turn out to be equal, which means that all three limits must be equal. They all must equal 1. Go ahead and add these two limits to the list of things you need to memorize. In the future, we will use these two limits to help us find other trigonometric limits.